Okay, welcome to video 3 of the While We're Stuck at Home series for AP Chemistry. This video is on salts, which are closely related to acids and bases, as we're going to see. Keep it simple with the definition for salts. They're just ionic compounds, which means a cation with an anion. The cations are usually metals or ammonium. The anions are all nonmetals or non-metal polyatomic ions like nitrate. When dissolved in water, these break up into ions, which can behave as acids or bases. And one thing to keep in mind, the salt of a strong acid and a strong base gives a neutral solution, meaning if you have something like hydrochloric acid, which is strong, and sodium hydroxide, which is also strong, but a base, you're going to get sodium chloride, which is a neutral salt. You have to look at the parentage when looking at salts. So the cation on the left is always coming from the base. So you have to think which base would potassium come from, and it's going to be KOH, which is potassium hydroxide, a strong base. The anion, in this case it's chloride, always comes from the acid. So HCl, or hydrochloric acid, is the parent of the chloride ion here. So you've got a strong base parent and a strong acid parent, which is going to give us a neutral salt. In this one, the sodium's coming from sodium hydroxide, the cation comes from the base. The nitrate, which is the NO3 minus, is coming from nitric acid, which is HNO3 and is a strong acid. And remember, you should know the strong acids and bases to help you do this portion. Okay, a basic solution is formed if the anion of the salt is the conjugate base of a weak acid. What we mean by that is you've got a parent that is a strong base and another parent that is giving us an ion that is from a weak acid. So strong base with weak acid gives us a basic solution. So when I look at sodium here, that's coming from the base, sodium hydroxide. The fluoride is coming from HF, hydrofluoric acid, which is a weak acid. We end up with a salt that is slightly basic. Over here, we have potassium coming from potassium hydroxide and acetate coming from acetic acid. The potassium is coming from a strong base. The acetate ion is coming from the weak acid. So you end up with a basic salt. In all of this, remember that Kw equals Ka times Kb. So that's going to help us out in some of the calculations that we do. When starting with a base, use Kb for your calculations. Let's look at the acidic side of things. An acidic solution is formed if the cation of the salt is the conjugate acid of a weak base. Otherwise, meaning you've got a strong acid and a weak base coming together, and they make a salt that is acidic. One example of this is ammonium chloride. Ammonium is an ion that comes from ammonia, NH3, which is a weak base. The chloride is the anion that is coming from the strong acid, HCl. So remember, anion always from the acid, cation always from the base. Here we have a weak base ion with a strong acid ion. We're going to get an acidic solution. Again, Kw equals Ka times Kb. In these instances, when we're looking at an acidic acid, we start with Ka for that. This is a table that, excuse me, just kind of summarizes everything. If the cation is neutral and the anion are neutral, the salt is going to be neutral. If the cation is neutral, the anion is the conjugate base of a weak acid. We're going to get something like sodium fluoride, which is basic. This is the conjugate acid of a weak base with a neutral anion. You'll get something that's acidic. And then if you have things like this, we have conjugate acid of a weak base, conjugate base of a weak acid. That's going to really depend on the Ka and Kb values here for that. You don't see a lot of that on the AP test, as far as I can tell, but we'll be ready for it. Here's a couple of other things. This is from the textbook that can help you guys remember these things. If the Ka is larger than the Kb, it's going to be an acidic solution. Kb is bigger than the Ka, going to be basic. If those guys are equal to each other, you've got a neutral solution. Here's some practice for some of the things that they'll ask us, possibly. One is to calculate the Kb values for these ions. So you've got to think of it this way. Acetic acid is breaking up into water, and it is giving us a conjugate base from a weak acid. So they're asking for the Kb value for that conjugate base. In this case, it's the acetate ion. So let's do that one first. We keep this equation in mind that I showed you earlier, and we rearrange it to get the Kb. And you guys know that Kw is 1 times 10 to the negative 14. The Ka is given to us as 1.8 times 10 to the negative 5. And we'll go ahead and divide those to get the Kb. So Kb for acetate at this temperature is 5.6 times 10 to the negative 10. Pardon me, in this instance, we've got a really low number there. So just keep that in mind as we go. Let's look at the cyanide ion example. Here we have, again, the need to keep this in mind. We're going to solve for Kb. We plug in the numbers and we get 1.6 times 10 to the negative 5 for this particular acid. Now notice the Ka values for these guys. There's a pretty big difference between the two of them. Acetic acid has a K of 1.8 times 10 to the negative 5, and hydrocyanic acid is 6.2 times 10 to the negative 10. It's much weaker, but you notice that its Kb value is higher. So you can keep that in mind as we're going along. Let's try one of these. This is calculating the pH of a solution of sodium cyanide. And they give you the Ka for hydrocyanic acid, and they say it's 6.2 times 10 to the negative 10. Now, you notice the sodium is coming from sodium hydroxide, which is a strong base. The Cn is coming from a weak acid, hydrocyanic acid. You saw how weak it was in the last one. So we're going to look at the equation for hydrocyanic acid and set up an ice table. The hydrocyanic acid is breaking down into cyanide, which is its weak conjugate base. So we're starting with a base, so we're going to need the Kb value. Unfortunately, they gave us this, but in the last slide, we figured out how to get this, the Kb. So we set this up with the cyanide as our base. It's reacting with water, which is the acid. We leave water out of the ice table because it's a liquid. And we end up with this acid and the base ion hydroxide. So our conjugate base, conjugate acid here. Notice we have X's there. Here it shows 0.75 minus X. I'm going to disregard that due to the size of the K. So I'm going to plug in all the numbers. The two X's on the right side of the ice table are going to get squared. The 0.75 is the equilibrium concentration of the cyanide going into this. And we get 1.6 times 10 to the negative 5. This is put in there as the Kb. So we need to solve for X, and X is going to be 3.46 times 10 to the negative 3. But you have to remember, if you go back to the ice table, the X is for hydroxide and not hydronium or H+ or the proton or whatever you want to say. So that is the concentration of hydroxide ions. What can we get from that? The pH. So if I negative log that, I'll get a pOH of 2.46. If I subtract that from 14, then I get the pH, which is 11.54. Now, this is just one way to get to the pH. Another way to do it would be to figure out the H+ concentration from this number using equations that I've shown you guys in class, and then taking the negative log of that to get the pH. I did it this way. Doesn't really matter as long as you get there and don't leave it in pOH, okay, for that, especially if they're asking for the pH. Okay, so here's another example. We've got a 0.3 molar solution of sodium fluoride, and it says the Ka for HF is 7.2 times 10 to the negative 4, and to calculate the pH. So on this one, you're going to run through all of the same steps that we did on the last one. I'm going to go ahead and put the answer in the Google Slides that are posted to Classroom for you guys. So go ahead and give it a shot. Check your answer. Ask questions. You can either post them here on YouTube, or you can email me, or just message me on Remind, and we'll get back to you. So that's a little bit on salts and how to do the calculations for those problems. The main idea is to figure out if that salt is acidic or basic, and then solve the problem from there. Again, it's like every equilibrium problem we do. Get a nice table going, get the setup for the K expression, and then work the algebra on that problem. Good luck.